Okay, in this next unit, we are going to be talking about waves and sounds, and we kind of simulated waves with our simple harmonic motion in the previous unit, but we didn't go super far into it as far as what a wave was. So this time we're going to go ahead and define all of those different parts and label them and discuss that in a little bit more depth. So the first thing we want to do is go ahead and label the parts of the wave on our diagram. And we're going to start by labeling the crest. And the crest is the topmost point on our diagram. So you're going to want a couple different colors, probably. Okay, so there's our crest, the very highest point on our wave. And so here's our complete wave. This is actually two waves, which we'll get into in just a second. The next part is the trough, which is the lowest part on the wave. And then the amplitude, so we use this word in our simple harmonic motion. The amplitude is that maximum displacement from equilibrium. So here we have a line going through the middle of our wave. So the maximum displacement is going to be from the top to the middle or the middle to the bottom. Both of those are going to be amplitude. And if you remember, this actually looked the same as our position time graph for our simple harmonic motion. And then the last one that we have is the wavelength, and the wavelength is one repetition. So going up, if we start at the center and we go up and we go down, we're back at the center, but we're not repeating ourselves yet. So starting here, we start repeating that motion. So this is the distance of one wavelength. So we can see on our diagram, this is one wavelength, here's our second wavelength, so this shows two wavelengths. So we have two different types of waves per se. We have a continuous wave, which is just one right after the other. And then we have pulse waves, which produces a wave or two waves. And then there's a rest, and then it produces more, and then a rest and produces more. So our two different types. So the difference between those two is that pulse is one wave at a time, while continuous doesn't stop. And there's different uses for each of those. But you just need to know vocabulary-wise that there's a difference there. And then there's also a difference between wave velocity and particle velocity. So on our wave here, our particle is not traveling along the wave. The particle is actually moving up and down or side to side with the wave, depending on what kind of wave it is. So this is a transverse wave, and so if we have a particle here, it's going to travel up and down as the wave moves to the left or to the right. Okay, so wave velocity is going to be how fast the crest moves. It's an easy indicator for your wave. And then the particle velocity is going to be the speed of the particle on the wave. And that's where SHM comes, or simple harmonic motion, comes into factor. So we've already done that one. So our box bouncing back and forth, that would be the speed of our particle, versus here the speed of the wave is how far does that amplitude, or how fast does the amplitude occur. So to get wave velocity, we have V equals lambda, and you make kind of a curve and then a line coming off of it, times F, where V stands for velocity in meters per second, F stands for frequency. Remember, we can alternate that with period if we're taking the inverse. And then the lambda is going to be the wavelength. And that's going to be measured in meters. So if we were to sketch a graph of wavelength versus frequency, these two have an inverse relationship. So the graph, ran out of room. So the graph is going to look something like that. Okay, so we have as one increases, the other decreases. So then moving right along, if we want to look at the velocity of a wave on a string, we have this formula, square root of t over m over L. And the t here is not actually period, which is kind of annoying, but you need to know this formula. So v is velocity, again measured in meters per second. So here we're talking specifically on a string. Not all waves are on a string. There's different ways that we can have them, going through the air, going through space, electromagnetic waves, all sorts of different kinds. But when we're talking about on a string, the tension of the string matters. So this is the tension. So the tighter you hold it, the more velocity you're going to get. And then this bottom part is called the linear distance or linear density. So this is the mass of the string in kilograms. And then the capital L is going to be the length of the string. And that's going to be measured in meters. So this is going to be a linear linear density, which is a little bit different. But we want to make sure that we're aware of that. So now the following lab data was taken for a wave on a long chord. The speed of the wave is 50 meters per second. What qualities should be plotted in order to create a straight line whose slope is the speed of the wave? Fill those qualities in the middle data table that's here. Make a graph to confirm that it is aligned with a slope of 50 meters per second. So this is our double check that our slope actually works out right. We know that frequency and wavelength are going to be inversely related, so we need to know what are we plotting on our x-axis and which one are we plotting on the y-axis. So if we look at our general formula, we know that our slope is velocity, and so if we want to plot, here is our x and here is our y, in order to maintain our formula, so v equals wavelength times frequency, whatever our x is and our y, we need to get that slope of 50. So you could do this a couple different ways. The important thing is that you want to do the inverse of one of them. So you have two choices. You can leave wavelength here as your x value and do 1 over frequency, or you can do 1 over wavelength equals your velocity times your frequency. And so this would be your y, your x, y, and x. And that was the bell in the video. So either one works. Go ahead and take some time, pause the video, and fill this in. And when we come back, I'll have mine all filled in, and you can check your graph. Okay, so if you graphed your data, you'll see that I actually had my variables backwards if we're looking at our formula. This should be 1 over wavelength, and this should be frequency, and then so forth and so on this other one as well. Oops, did that backwards. So this would be wavelength 1 over frequency. Okay, there we go. That should make your line better. And you'll see that that's what I did up here in my table. And then next thing we need to do is draw a line of best fit. And these line up pretty well. So the next thing that we need to do is identify the longitudinal and transverse waves and the difference between these two types of waves. These are our two basic shapes. We have longitudinal, where we have the pushed together parts and the stretched out parts. And then transverse is where you have that up and down wave, what we're used to seeing. So transverse waves, the particles are going to move up and down. That's perpendicular to the wave. So here we have our particles moving up and down as the wave transfers along. And in longitudinal, the particles move side to side, so they move this way, which is parallel to the wave as far as the motion goes. And that's important because that has to do with how the wave is formed and how we perceive it. And so transverse waves, this is like water waves. And then longitudinal, an example of that will be sound waves. Although often we illustrate sound waves as transverse waves because this is a lot easier to see than our longitudinal wave. So transverse waves have crests and troughs. That's what we identified at the very beginning. And then longitudinal waves, so we're going to draw stretched out and then like a part that's together and then stretched out, and then a part that's together and then stretched out again. So what these have, they have an area of compression. And then they have a stretched out area, which we'll do over here. Okay, so they have compression and stretches. So here we have another compression, and then here we have stretch. And so these alternate similar to the way that your crest and your trough alternates. So in the example of your transverse wave, what we wrote up here, this would be our ocean waves. And our example of a longitudinal wave would be the sound waves. So now we get into reflection and interference. So when a wave runs into something or strikes something that behaves differently, different densities or anything like that, it's going to behave a little bit differently. So when a wave pulse, and we're going to be talking about just the pulses. So remember that if we look back at our first page, this is what we're talking about. Just a single wave, what happens? Because when waves overlap, different things happen, which we'll get into. But we're going to just talk about if I send out one wave and it hits a wall, what happens? Okay, so when a wave pulse strikes a wall, the wave pulse is going to reflect back, and it's going to be inverted. Okay, so that means upside down. And you're going to be able to do this in a lab and see what exactly happens. You should be able to see these things. Then when a wave pulse reaches a free end of the string, so here it's hitting a hard surface. When it reaches the free end of a string, it will reflect back, so bounce backwards, and it will be the same. So if it was above, then it'll reflect back above. If it was backwards or upside down, it'll reflect back upside down. The wave front, this is some vocabulary that we're going to use, is the particles at the beginning of the wave. Okay, so, beginning, there we go. So if we have our wave going like this, this is going to be the wave front, the particles at the beginning. Interference is going to be two waves overlapping. the principle of superposition is that when those two waves interact with each other and overlap, the amplitudes of the waves add together. So if you have a negative amplitude, then it will subtract from the other one. There are two types of interference. There is constructive interference and destructive interference. Okay, and those are our two basic types, and we're going to go into those more on this next page. And you need to be able to draw these two different types of interference. Okay, so when the crest and troughs of two waves interfering are aligned, so the crest and the trough, top part and the bottom part, or sorry, the tops are aligned and the troughs are aligned. So here's your crests are aligned and your troughs are aligned. Then we say that the waves are going through a constructive interference. And so constructive means that they're going to add together. When the crest and the troughs of two interferers are completely misaligned. So here we have a crest and a trough lined up, and then here we have another crest and a trough lined up. Then that is when we have destructive interference. Okay, so this is, we're going to talk about speakers. So we're talking about sound, but notice we're illustrating it as a transverse wave. And that's because the transverse wave is 10 times easier to draw and easier to identify those crests and troughs and whatnot. So the boxes represent speakers that are in phase with one another. That means that they create crest and troughs at the same time. The man is a different distance to each speaker. The vertical lines are half of a wavelength apart. In each diagram, complete both waves and then say whether the man hears loud or quiet sound. So if we continue this wave, okay, so each one is half a wavelength long, so that means it's going to be like the little hill, then the valley, and then the hill. Okay. So here, what we see is that our crest and our trough lines up, and our crest and our trough lines up here. So here, these two waves are going to cancel out. So the wave cancels. And so the sound that he is going to hear is nothing. It's going to be very, very quiet. So if we do this one down below, do up, and then we do down, we do up, down. Okay, so we draw in our waves, and we look at what things are aligned. So here we have a crest and a crest align. Here we have a trough and a trough align. So this is going to be the waves build. And so he's going to hear a loud sound. So go ahead and do the next two on your own. Pause the video, and when we come back, we'll discuss a rule based on your result. Okay, so for this first one, where we were 1.5 wavelengths apart, you should get that they were quiet because we have destructive interference. And on the second one, 2 wavelengths apart, then we have constructive interference because our crests and our troughs line up. And so we end up with a louder sound. Okay, so when we hear a loud sound, we end up with constructive interference. Okay, so this is when the speakers are whole wavelengths apart. Okay, whole wavelengths apart. And we hear a quiet sound or no sound. That's going to be destructive interference. and this is when the speakers are half wavelengths apart. So unless they are completely a whole wavelength apart, we're going to end up with a quieter sound. And this is why placement of your sound systems is so important in rooms, is because you get those soft spots whenever the speakers are not lined up properly. And so there's certain ways that you have to set up the speakers for a sound system. Okay, so now we're going to go through the wave reflection and interference activity. And you're going to be doing this in a lab and simulating this, but I want to go ahead and go through it. So using video analysis, we're not actually using the video on this. Draw the last 3 frames of the animation of the waves on the spring in each activity below. So I'm just going to kind of show you what's going to be happening here. Let me switch to color you can see. So a student sends a wave pulse towards another student who holds the spring. So this is going to be like hitting a wall. And we would expect this wave to come back inverted. So here, it's going to hit the student, and we're still going this way. And then it's going to come back the other way. And it's going to be upside down when it comes back that other way. And then if we have it hooked up to a ring stand, okay, towards a pole, the spring can slide on the pole. This is, let's see here, the words that we used before. It says reaches a free end of string. So this is going to be like a free end. Okay, so it's going to hit our pole right here. And then when it comes back, it's going to be upright. Okay, so if it hits something solid, it's going to be inverted. If it hits something free, it's going to be upright. So on 3 and 4, we're looking at interference. Okay, so this right here, if they're both positive amplitudes, this is going to be a constructive interference. Okay, constructive interference. And so when they align up, because here they're traveling towards each other, when they align, you're going to get a wave that's larger than the 2. And they're going to be going both the opposite direction. So they'll travel towards each other. And then when they hit, it grows. And then once they go through each other, you have the 2 waves, their original sizes again, moving on as if nothing ever happened, traveling towards each of the students. And then on this last one, they have opposite amplitudes, so this is going to be destructive interference. And once they hit, we're going to see nothing happen. Okay, so the waves overlap and cancel each other out. Then this one below is going to continue on its way. So down here it's continuing. And the one above is going to continue on its way. And then we see that same thing, they continue. So when they interfere with each other, it doesn't change the wave. Excuse me, it doesn't change the wave. It simply just alters it for that brief moment, and then it continues on. So that's kind of just a general sketch of what happens with our interference. Now we're going to actually go and look at the waves themselves on a graph and add them together. So that's going to be our next example. So in each of the situations depicted below, 2 wave pulses move toward each other. One is bound by points A and B, and the other bound by A prime and B prime. So that's just distinguishing between the 2. Draw what the combined pulse will look like when A and A prime are at the same point. So for the sake of our visualization, we're going to draw this in 2 different colors, and then we're going to overlap them and then draw in the new wave. So A is going to look like it's got 2 up and then 3 over, 2 down. So this is the original A. And the original B is going to look like this. It's going to be like this. So when we draw our combined wave, here we're going to add all of our amplitudes together. So this becomes 4, and all the way over here to 3 is 4. So here's our new wave. And then here we've got 0 plus the 2. So here's the new wave that we have. Okay, I'm going to reinforce this with some blue pen. All the colors kind of blend together a little bit. Okay, so we've got A, we had constructive interference and still constructive interference all the way across. So we can do the same thing for this next one. This one's a little bit more complicated because we got that stair step. So we're going to rewrite that stair step over here. It goes up 3. And then we've got this downward one here. So now we have a negative amplitude. So we've got down 3, over 3, up 3, like that. Okay, so when we add those together, we've got 1 minus 3. So it'll give us our negative 2. I'll go ahead and do this in just the pen. Okay, so negative 2, and then 2 minus 3, so that's going to give us a negative 1, and then 3 minus 3, that'll bring us back down to 0. And so we can see our wave here is going to look like a little, almost the opposite of our stair step. And this next one's going to look really weird. So we're going to do the same thing. We're going to draw our original waves so we can overlap them. Okay, so I'm going to go ahead and draw in the prime. So it's up 2 because it's nice and easy. And then I'm going to draw my regular, just the A. So it's got 1 line in the front, so we're going to complete that little angle. Now on this one, I would suggest not worrying about the triangular part so much or the slanted part so much. I would worry more about how this is going to work because this is going to add together. And you'll just have to do the diagonals. So this is 2 and this is 2, so those are going to cancel out to make 0. The purple is at 0, the green is at 2, so it's going to stay here. And same thing here. And so this change, this is going to be 0. We're going to connect that angle, and then go back to our 0. So you have to look at each point individually and draw your new wave from there. Okay, and that'll conclude today. Tomorrow we're going to talk about standing waves.